Okay, I think we can start. Can people in the last row hear me well? Yes? Okay, my name is Joanna Rutkowska and I would like to tell you about passive covert channels implementation in Linux kernel. This is going to be a little bit long lecture, like 2 hours, but I will have some live demos, so I hope you will not fall asleep. So first, I think everybody knows what are covert channels, so they don't require an explanation. They are just communication channels which can be used by malware, which is installed on some compromised computers to steal some information like sniffed passwords. So people who wrote malware are interested in communicating the information which was stolen by their sniffers, for example, how to communicate that information in a stealth manner to the attackers. So I'm going to focus on passive covert channels, and by passive covert channels I mean such covert channels which do not generate their own traffic. So they only change some fields in the packets which are normally generated by the compromised computer. So the user, for example, is browsing the web, and the passive covert channel engine, which is installed somewhere in the kernel level, just silently changes some fields in the network packet, in the packets, in the outgoing packets, and puts some secret information there. So imagine this simple scenario. We have a compromised computer. Let's say it's a desktop computer. So it's like this is a company network, and they've got desktop computers which hold some interesting informations. The attacker is here, and the attacker is controlling the ISP. So the attacker is just an engineer who works for the ISP, like ISP malicious employee. The attacker has managed to install some sniffers and other malicious software on this compromised computer, like CEO of this company computer. So this sniffer is sniffing some, let's say, web passwords. And now we face the problem how to secretly communicate the sniffed passwords to the attacker. So the solution I will show you at this lecture is to change some fields in the packets, but fields in the packets which are normally generated by this user. So we can see this blue line which shows the, in this example, these are web requests made by the user of this computer. And here we see changed fields which are sniffed here, and the information is transferred to the attacker. Is it clear idea? So this is very simple. Like we don't need to spend much time on discussing this. What is more interesting is how to implement a backdoor or a passive covert channel, so that it will be able to intercept all outgoing packets, to change them, or to change some fields in the packets in such a way that it will not break the communication. For example, we could change the ISN numbers in the outgoing TCP packets, but then if we do it not carefully, we will break the communication, because after changing the ISN of the first packet, when we get the ACK packet from the server, this ACK packet will be discarded by this computer. So in the later part of this lecture, we will be discussing the solution which will change ISN numbers, but will change it forth and back. So it will change ISN, original ISN, to passive covert ISN, send it to the network, then it will intercept the ACK packets, change their ACK number, acknowledge number again, so it will match the kernel ISN, and then change all sequence numbers in all consecutive TCP packets. But first, I think it would be useful just to discuss the trace of the packets in the Linux kernel. So I will be discussing how the packets are handled by the Linux kernel from the interface to the socket, and from the socket to the interface. We will spend like 10 minutes on this. Although it's not necessary to understand all the following things, but I think it's good to know where our passive channels can be located. So from this point, for the next 15 minutes, we'll focus on the newer Linux kernels, that is 2.6 and 2.4 greater than 2.4.20. In 2.4.20, the network interface has changed a little. Don't be scared of this slide, it's the most complicated slide I have. Yes, it is. So this is the result of my exploration of kernel sources with Vim and Ctacs. And this is the first part of handling the network packets in Linux kernel. This yellow rectangle is a network driver. We see a network card. And let's imagine a SYN packet is coming to the interface. Well, the interface generates an interrupt. This is not always true because newer interfaces do not generate interrupt with every packet. They like collecting few packets and then generate interrupt, but it's not really important here. So the packet came to the interface generates interrupt, and driver provides interrupt service routine which handles the interrupt and does actually two things. Well, it actually calls netef schedule function, which does two things. It enqueues a device pointer to the processor-specific queue of the devices, and then it raises a software queue, netrx software queue. And then the service routine completes. This is a little change comparing to the older kernels, where we don't have CPU-specific queues of devices, but rather the ASCII buffers are enqueued in the queues. So when the kernel has some time, it serves the software queue, and software queue is served by netrx action function, which does two things. The queues the device pointer. It's a net device, structure net device. Queues the device pointer, and then it calls poll routine from this device. And poll routine is a device-specific function which retrieves the SK buffer. Well, not. It actually retrieves the raw data of the packet which came to the interface. It builds the ASCII buffer around this raw data. ASCII buffer is just a raw packet surrounded by some headers telling about its length, about protocols, this kind of things. And then poll function is calling netef receive ASCII function, which is a standard kernel function. And this is the first interesting point for us, because now the netef receive ASCII function is making a decision which protocol should handle this ASCII buffer. And this decision is made by looking into p-type all and p-type base tables. And in the later part, we will actually add our own handler of protocol, which will get the packets from the interface when the packets come, when the packet comes into the computer and when the packet is sent over the network. So we will have control over the packets. And this is the first point where we can have the control because this is based on the table which we can add our own pointers. So let's follow the IP path. So this was TCP SYN packet. So it's an IP packet. So we are going to IP receive function. Is it clear up to this point? If you have any questions, just don't hesitate and interrupt me. Okay, so we are in the IP receive function. The first thing IP receive function is doing is calling the net filter hook, the pre-routing hook, which can return one of few decisions for the packet, like drop the packet, accept the packet, steal a packet, and that kind of things. Net filter framework is another good target for the attacker for adding his own handlers of the packets and to change the packets, to change some fields in the packets. Okay, provided the IP pre-routing hook returns accept, we go to IP receive finish function. Which makes the routing decision, and the routing decision is written into DST field of SKB structure. SKB structure is the SK buffer actually. And then, depending on the routing decision, we have few options. We can deliver the packet locally if it was destined for the local system. We can forward it to another computer if it was destined to another system and the forwarding is enabled, and some other options which are not interesting for us. So here we have local deliverer. Local deliverer is made by IP local deliver function, which first checks if the fragmentation is needed. If it's needed, IP defrag is called. And then IP local in net filter hook is called, which again can return one of few results, like drop the packet, accept the packet, and that kind of things. So provided it returns accept the packet, we are going to a local deliver finish function, and then based on the protocol field, the protocol field in the IP header, we are going to TCP, UDP, ICMP, or something else. That something else could be a row socket, IP row socket, which is very different from PF packet row socket, which I will discuss later. Okay, this is the second option. This is the forward option. So if the packet was destined not to the local host, we call IP forward net filter hook. Then if it accepts the packet, we call IP forward finish. Then we call IP output. If the MSS of the interface we are going to leave the computer is less than the MSS of the incoming interface, we are fragmenting the packet. Then we have finish output and post-routing net filter hook. And if it allows the packet to leave the system, we are calling finish output, and then we send the packet to the world. And also, when we send the packets from the local system, so we are the local process on the system, the packets go to IP output function. So this is here is a TCP layer, UDP layer, ICMP layer, and they all go here, and the same path as forwarding packets. And this last part of the packet journey, so this part is shown on this picture. So we've got IP finish output. Then we use a standard kernel devq xmit function, which queues the devices to the queue. And we've got a qdisk restart function, which is constantly called and which retrieves the devices from this queue, and it calls devq xmit need for each retrieved pointer here. And this is a very important part for our lecture. This function is calling all registered packet type handlers from ptype all list. We will see ptype all list within 15 minutes, I think. So this is the list where we can add our own handler. So we are adding our passive covert channel handler to this list, and thanks to this function, our handler will be called for every outgoing packet. And then we have a device-specific hard start xmit method, which sends the packet over the internet, Okay, do you have any questions to this short review of packet paths in the kernel? Anybody disagree with this map? Well, I can make mistakes, so if you have any comments, feel free to tell them now. Okay, so we are back to our, no, we are not back at the moment, but we will be back in a few minutes. So from this previous review, we can see that we have two options for adding our own functions for handling the packets, both incoming packets and outgoing packets. On this lecture, I will focus on adding a p-type handler or packet type handler, but we can implement all these things also by adding net filter hook. But I'm just thinking that p-type handlers are more difficult to detect. Like we can very easily detect additional net filter hook in the kernel. I will show you this later. But detection of p-type handlers, like even the listing or enumerating all the registered p-type handlers in Linux kernel, is a very hard task. And of course, I will discuss how to detect them at the end of the lecture. So p-type handlers are held on two lists, p-type all and p-type base. So just to remind you, p-type all and p-type base, those lists are scanned at this point, where the netef receive skb function is looking for appropriate handler for the packet which just came into the interface. And the other point is here. So it's called the p-type all. Only p-type all list is scanned for all outgoing packets. P-type all is very simple. It's just a head of two pointers. These are all double linked lists. So if we start TCP dump on our Linux box, TCP dump opens raw sockets. These are not IP raw sockets, but these are PF packet raw sockets. And PF packet raw sockets are actually adding, well, the kernel part of the PF packet socket adds a handler to this p-type all list, and this handler is pointing to packet receive function. Within an hour, on one of the live demo, I'm gonna show you this packet receive function and a list of this registered hooks. So by registering packet receive handler, PF packet implementation can make sure that it will handle every incoming packet. Also, it can make sure that it will handle all outgoing packets because of this function on the previous slide. Ordinary protocol handling function like IP receive, ARP receive are registering handlers on this list. This list is 16, has 16 slots, and each protocol gets its own number. It's a 2-byte number, and there's a simple hashing function which converts the protocol number, a 2-byte number, to the one of the 16 number here. So, for example, at the first entry, we can see a handlers for IP protocols, and on this 14th slot, we can see IPv6 protocols. And if we could look at this list in our Linux box, we would see something like IPv6 receive function registered here. So we are going to see this. Okay, so now a more practical part. Adding our own packet type is very, very easy. All we have to do, we need to fill this structure. This is a documented structure. We should put a type. A type of protocol we are registering the handler for. So we will put ptype all. Sorry, not ptype all, but this constant. eth IP all, which is defined in some header file and is equal to some number, which I don't remember. So we are putting this number here. We are putting the device we are interested in watching. Or we can put null here to just watch all the devices. And here we put the pointer to our function. And that's all. Or we can put some private data, but they are typically not very important. And then we have two documented kernel functions for adding and removing packet type handlers. One is def add pack, and the other one is def remove pack. Both functions takes a pointer to the structure. So this is all we have to do to add our own function. This is a simple code. Of course, we have to do this in kernel. So this is the code which we can put in the init module function of our LKM module, right? So don't try to compile the user on C program like this. Any questions up to this point? Okay, so we are back to our passive covert channels idea. So we see that we can put on this computer additional packet type handler, which will handle our outgoing packets, and will change some fields in those packets in a smart way. So we are going to do this. This is the picture which you are very familiar with, I think. This is a TCP header, and it, of course, has two sequence numbers fields. Both are 32 bits long. So this is the sequence, and this is the acknowledge number. And of course, the sequence number, which is transmitted in the first packet of the connection, is called the ISN number. This is also a very well-known picture. This is the handshake of the TCP connection. So the client sends the SYN packet to the server. It chooses randomly a sequence number, which we'll be using for this peer. So this is ISN1, and sends the packet. If the TCP port is open, the server responds with synack packet, it puts its own ISN number, so it's ISN2. This is chosen by the server, and it also displays the sequence number chosen by the client in the acknowledge number, +1, because syn packets takes one sequence number. And finally, client acknowledges the connection by sending ACK packet with sequence number equal to ISN +1, so this time it retrieves here, and it also responds with ACK number which is equal to ISN2 +1. So nothing interesting in this. Is it clear? Yeah. Okay, so our passive covert channel, the simple proof of concept which I'm going to show you in a moment, is going to change ISN numbers in all TCP SYN packets leaving from the compromised computer. Then it will also change back the ACK numbers in all incoming TCP connections. This is necessary because if the PCC module didn't change the ACK numbers, so the kernel will drop the ACK packet because the sequence number will not match the ISN number. Also, it needs to make sure to change sequence number in all consecutive packets from the same connection, because we first changed the ISN number, so if we didn't change the sequence number of other packets, the server this time would discard the connection because the sequence would be different from the ISN number. Is it clear? Okay. We can send 4 bytes per TCP connection. So this is not much, but when we consider HTTP traffic, when user makes lots of Google requests and then searches extensively on the internet, it's quite reasonable amount of data we can send, like let's say 1 kilobyte in 1-2 hours. And because our passive covert channels are primarily designed to send the passwords or that kind of things, it's quite enough, I think. Okay, so this is the picture showing the relation between kernel, passive covert channels module, and the internet. So when the user process when the user process wants to connect to the server, it calls a connect system call. Connect system call makes the kernel to generate TCP SYN packet, and the kernel, actually the function secure TCP sequence number, is putting the kernel chosen ISN number here. Our kernel module, which is registered as p-type handler, intercept this packet, overwrites the ISN number with its own ISN number, which contains some secret data we are going to send, and then sends the packet to the internet. Then, when the synack packet comes back, first the passive covert channel module handles the packet. It now replaces the ACK number, not sequence number, but ACK numbers in that case. Well, it not actually replaces it, but it subtracts from this number this value. So the passive covert channels module remember for each TCP connection the difference between ISN CC and ISN original. We can call it offset. So here we are subtracting the offset, so we have the correct ISN numbers. So kernel gets the TCP SYN ACK packet with the correct ACK number. Right? I'm sorry, what? Okay. And finally, when the kernel answers with ACK packets, or not only ACK packet, just any other TCP packets from that connection, the PCC module must detect that this packet belongs to that connection, must find out the offset, and adds the offset to the sequence field. And of course here, somewhere in the internet, we have a sniffer which just sniffs the ISN, the ISN numbers from the connection. So it gets the secret information. Of course, the information here is encrypted, but I will tell about it later. Is it clear? So this is the structure which is used by this simple implementation I'm going to show you to track the TCP connections and to remember the offsets.
Can I ask a question?
Where are you? Okay.
How do you make sure that the covert channel module gets hands on the packet before the kernel does? I mean, I'm not familiar with it.
I can assure you.
Okay, I know. I'm pretty sure. I'm just wondering about the mechanism that you use for that.
Yes, I will show it to you. Well, as I said, our PCC module will register its function, its handler, as a p-type handler. P-type handlers are handled here. And because our p-type handler will be on the p-type all list, not on the p-type base, IP receive function, so the standard kernel function for handling IP packets, which actually, yeah, this is the kernel, yeah, is on the p-type base list. When you look at the kernel sources, the p-type all list handlers are scanned first, then p-type base handlers. Any other questions? We've got plenty of time, so yes?
Yeah, just a simple question. What happens if you have a kernel that does not support loading modules?
Well, this is another story of how to insert code into the kernel. Like you can use a kernel overflow for this purpose, for example. I'm just not focusing on this. Like I'm assuming that we have the privilege to insert kernel code into the kernel, to insert code into the kernel. I'm going to tell a few words about 2.6 kernels and about difficulties with the new module scheme and about hiding the modules at the end of the lecture if I will have some time.
One more question.
Okay.
Why are you not using the ID field in the IP header? Because then you could.
Why didn't I use? Why don't you use?
Yeah, it's smaller, but you can leak data with every packet, not just with every connection.
Well, it's not always random. Not always random. Sometimes it's incrementally, well, it's incremented sometimes. Yes? Besides, it's only 2 bytes wide. ISN numbers is 4 bytes wide. Yeah, because some devices could just, you know, null it also. But I think that the biggest problem is that, for example, some Linuxes are not making it random. So it would be very easy to detect the covered channel because, for example, we've got 2.4 Linux, which, as far as I remember, has incremental numbers. So then administrator looks and see random numbers here and thinks something is wrong. And ISN numbers must be random by definition. Another candidate, a good candidate for this would be, for example, HTTP cookie, I think, or some other fields, which should be random or is chosen arbitrary and yeah, and by definition. Okay, any more questions? Okay, so this is the structure which my little program is using for tracking the connection. So this is just the four numbers describing the TCP connection. And also we've got the offset, which is saved after the first, in the first packet. After the first packet ISN is changed, yes? This is the offset between, this is the difference between this and this. So our passive covert channel simply scans the list of the kernel infrastructures. Now it's like our passive covert channels gets a packet, checks if it's a TCP packet, and then looks at this list, tries to match the packet to this description. If it matches, then depending if it's an outgoing or incoming packet, it will subtract or add the offset to the sequence or ACK field. Also, it would be nice if we have a nice method for freeing those kernel infrastructures, because after running on the compromised computer for a few days, we will have plenty of memory consumed by those kernel infrastructures. So we need to have an easy method for detecting kind of connection. This is somewhat complicated task, because to implement it properly, we will need to implement a TCP state machine. So just by observing the packets, we will know when the connection is actually closed. Because there are so many ways of closing TCP connection. Another solution which I took, which is much easier, is just scanning TCP hash info from time to time. And TCP hash info is actually the kernel structure which is used by proxy system to feed the proxnet UDP, proxnet TCP, at that kind of files. But proxnet TCP only, because UDP hash is for proxnet UDP. So when we are reading proxnet TCP, we are just the kernel functions which handles proxy system is just reading some information from TCP hash info structure. The nice thing about using this is that this is the exported variable. So we know the address of this TCP hash info function. So from time to time we remove all dead TCP connections. Well, actually not from time to time, but with every TCP send packet. So we detect TCP send packet, we first look at this TCP hash info, we are removing that connection, and then we are serving that new TCP send packet. Okay, so for any communication channel which we would like to use in the wild, we need some reliability mechanism which will take care of reordering the packets and retransmitting the lost packets and that kind of things. And the nice thing that about TCP protocol is that it already provides some reliability mechanism, but we cannot use them directly, of course. But we can exploit the nature of TCP protocol to make our life a little bit easier. So I'm gonna describe you the protocol I'm using in this covert channel, which is a little bit interesting because we have the sender, we have the receiver, and the receiver is passive, but we have the retransmissions. So we have the mechanism, the sender can know which packets are lost. Although the receiver is completely passive. It doesn't respond with the packets like ACK or just packets which are saying which packets were not delivered. It's completely passive. This is the simple protocol overview. The protocol first tries to send n packets. Maybe not n packets, n portions of data. Because of the protocol, the ISN field which we are using is 32-bit fields, but we are using only 3 bytes of them, and 1 byte is for control byte. Is used as a control byte. So let's say we've got plenty of bytes to send. Like we sniffed lots of passwords on our compromised computer. So passive covert channel has some data to send.
Just a question, please.
Yes.
If I use a local packet capturing, what numbers I see? Do I see a different acknowledge number if I do local capturing and the capturing in the net?
I'm gonna discuss local capturing in, let's say, half an hour.
Okay.
This is a good question, and I'm going to tell you how to cheat local capturing. I'm gonna show you some working code for cheating local capturing. So we've got the simple protocol. We are sending all the data we have, but not more than n blocks, in n packets. So we send 3 n bytes. Every line is one TCP send packet. So every line is one TCP connection. After we send n bytes, n packets, so we send max packets per block. I define block as, let's say, 16 packets, because I have my own sequence numbers, which are different from TCP sequence number, just to make sure the reordering is working well and to know which packets we should retransmit with a covert channel module. Then we retransmit all the not acknowledged packets. So now you should ask, how is it possible that my sender knows which packet was not received? Anybody has an idea how the sender could know which secret bytes was not received by the receiver? And I remind that the receiver is passive. Yes?
You get back your packet because you exploit the nature of TCP, you
Yes.
just told us?
Yeah.
So you get back the information with the sequence number?
Yeah, actually you're right. So because we are sending our send packet here, so our secret message here, and I said 1 byte is for control byte and the other 3 bytes are data byte, and the control byte contained the PCC sequence number, so this number is echoed, is displayed back in this field. So, and this packet is sent just by the kernel of the receiver, not of the receiver, it's just by the server kernel, yes? The pure computer kernel. So the receiver does not generate this packet. This packet is generated by the computer we're just communicating, the user is communicating with, like Google.
One question. What do you do if the packets got reordered? So if the sender sends packet A and then packet B,
Yeah,
and
I
it
just
got
said-
reordered somewhere.
I just said that I'm maintaining the a little sequence number. So the receiver just takes care about reordering the packets. So we know which packets was not acknowledged. So after we send n bytes of packets, we resend the packets which were not acknowledged, and then we have the state that all packets were acknowledged, or some new bytes. We have some new bytes to send. So we are sending either new bytes or just resending the packets which were not acknowledged again. Then we have the state, all packets are acknowledged, and we are sending a special ESN which tells start a new block. So reset the sequence number, the PCC sequence number. I'm going to show you this first. So this is the ISN number which PCC is using. So we are sending 3 bytes, and we have a control byte. Control byte has a sequence number, a private sequence number, which is used for the reordering packets and for detecting which were not, which were delivered successfully, because the sender can detect which packets were delivered just by subtracting this set from the set of all packets. It knows which were not delivered. And also we've got two bits for saying how many bytes are actually sending here, because not always we need to send 3 bytes. Sometimes the sender can have only 1 byte to send. So it would be waste of time just to wait until we will sniff another 2 bytes of password. So we are just sending 1 byte, and we are saying 1 byte, and this data is discarded then. If it's 0 here, it means a control byte, a control packet. A control packet is, for example, ISN new block. This is a protocol diagram which is probably more readable. So this is the decision which covert channel's handler is doing when receiving a new TCP send packet, and it's just wondering what to do with this packet. So if it has some bytes to send and the block is not complete, we are just sending ISN, we are just sending data, like snippet password data. If the block is complete, we need to send ISN new block. But first, we need to make sure that we retransmit our non-acknowledged packets. Okay? If we have nothing to send, because no more password sniffered, so we have nothing in the buffer, but we have a new ISN packet and we need to do something with this, we first check if we have something to retransmit. If we have, we just retransmit them. If we don't have, we are sending a special control packet ISN empty, which is a sign for the receiver that there's nothing interesting in the packet. 2 special packets, ISN new block, ISN empty. This is 0. This is a magic, and this is some random data added to the packet. Random data are adding because I'm using encryption, and I would like to make sure that the ISN numbers are not repeating, so they are not betraying the channel. Any questions to the protocol? Okay.
Okay. Do you have any special control packet to detect if, for example, the channel is open? For example,
do I have any special packet?
I try to explain it. So you are sniffing the traffic somewhere at the ISP, and you don't know when the traffic will start. So you have to recognize if you're
Yeah, this is the ISN new packet, ISN new block. The receiver just looking for the ISN new block packet. When it receives the first one, it assumes that the sender was turned on and is now sniffing all the traffic. Yes?
Okay. Okay.
Yeah, I could create a special start packet, but just for simplicity, I'm using this. Okay, the last thing I would like to tell you before the live demo is the encryption I'm using. So we need to use encryption, because if we didn't use encryption, network IDSs or inquisitive administrators would see some ASCII data in ISN numbers, which would betray the channel. So this is very, very straightforward. Both sides share the common key, so it's a symmetric encryption. And what I was most concerned about the algorithm I've chosen for this was its randomness. So we are not care about about being secure, because I doubt anybody would like to crack the cipher. It's just going to be similar to the ISN numbers which are generated by Linux kernel. We've got a little problem because most of the algorithms are using at least 64 bits on input and output when we are encrypting something, but we have only 32 bits to encrypt. So the solution is on the slide. This is the plain text. This is the ISN generated by the PCC protocol. And this is the result. To make the result, we are generating something like one-time path XOR. But to generate it, we are using this. Or we can use some other like AS or whatever. The input for the encryption algorithm is made of 4 fields which are in the packet. Source address, destination port, and the source port. These are the only fields I can use for generating the for this key, because I need to make sure, well, if only a receiver was the peer which needs to decrypt the traffic, I could use any of the fields from IP and TCP headers to generate the key. But we need that the sending computer also decrypts the ISN numbers. The sender needs to decrypt the ICK number. So the sender needs to decrypt the number here. Yes? So we are encrypting it here. The receiver can obviously decrypt it because it can generate the XOR key just by looking at the packet, but the sender also has to decrypt the ACK packet. So the only fields which we can be sure that will be returned back here are the source port, destination port, source address, and destination address. And we are XORing them just to avoid the problems with reversing their meaning. Like when we are getting ACK packet, just a minute, source port became destination port. Yeah, just a minute.
I have one more question. Why does the sender have to decrypt anything?
Because it needs to know which packets were received. And it can know it by looking at the sequence number in the ACK number, in the private sequence number, which is put in the ACK number of the TCP ACK packet, which comes back.
Well, but it only needs to encrypt it and remember the encrypted value. Am I not right? Why should it decrypt it back? It has the encrypted value already.
Because you don't know which ACK packets you get in because of the reordering. Like you could send, let's say, the user starts few TCP connections. Like this user, this is the server. So few send packets were sent. In each send packet, a different data was put. So each send packet has different sequence number. A private sequence number, not the TCP sequence number, just the PCC sequence number, yes? So they were sent, and now we are just, okay, it might be used, yeah, I think we might exploit the kernel infrastructure for this. I think you are right. But it's probably easier to decrypt it than to hold it. Yeah, so what is he saying is, he's saying that we can just save it here, like we can just save the sequence number here, right? Yeah, so we can just match the packet and we just know it, so without decryption. So this is the alternate solution. But because my simple proof of concept is not doing this, it's just decrypting the packets, so that's why we are using only those 4 fields, and that's why they are XORed. So we got the 64 bits key, we are using the first 32 bits to make the one-time byte XOR, and we are XORing this and we are sending the sender net. Yeah, this is what I was saying, and this is not really necessary as he said. So this is, we are sending SYN and we are getting back ACK packet. So my implementation just decrypts it and gets the sequence number. Okay, the no-show is the name of the code. So this was the secret language of the Chinese women. It was disguised as a decorative mark, so I thought it would be a good name. So it has some features like on-the-fly sequence changing, reliability layer, PF packet cheating, which I'm going to discuss in half an hour. And it's only for 2.4 kernels. I will discuss 2.6 kernels at the end of the lecture. Can I ask you to switch to this microphone? So I've got 2 Linux boxes here. One box called Alice is the desktop of the unsuspicious user. What's happening? I'm sorry, I was not looking at this. What happened? I pressed the revert, yes? Did I? No, I had a snapshot of well-configured system. Let's try this one. Oh. I was just checking it half an hour before my lecture, and everything was working okay. So. Oh my God. But we lost Alice. It's what? No, I had configured it for this network, so it would be faster if it worked like this. Okay, so gate is the, maybe I will show you the slide first. VMware eats lots of memory. So this is the gate, this is Alice. Yes, and Alice will be compromised. We are going to compromise Alice with our sender, and we are going to get the information on the gate. So we are just a malicious employee of the ISP, so we have the access to gateway. And Google, the Alice Alice is going to make some requests to Google or some other web service. Okay, so first I will install the receiver on the gate. I will intentionally disable the encryption so we can see the protocol data in ISN numbers first. I also going to tell that about which IP, on which IP is the sender installed. I think it's like this. So this is a simple proof of concept. This PCC doesn't contain any sniffing modules. It just exposes a proc file system catalog, which we can read the sniffed message and we can put the message we want to send. So now we have no message. Then we are going to Alice. So now we are the bad guys and we are going to compromise Alice. Yeah, without cipher. And that should be all. Okay, so now, well, imagine we just sniffed some secret password. Oh, can you see this? Yeah. Okay, so we have secret password to send. I would like to show you together the window with the web browser and with the TCP dump. Can you see this put the window? Okay, so we start TCP dump here. We are going to sniff on ATHO, and we will be looking only for SYN packets. So the magic command is something like this, maybe. Okay. So now the AI is not suspecting anything, they're just browsing the web. Oh, one more thing. What we can see here is a TCP packet dump. This was the SYN packet to, maybe it was Google DE maybe. And here is this sequence number. So if we decrypted 736170, this is some ASCII data. We missed the first packet because I forgot to put the -X switch on the TCP dump, but the first packet was the start new block. And this is the return packet. Okay, and we see our ACK number here, which is equal to this number plus 1. So everything works like in the real TCP connection, but these are the data put by the covert module. Just we can check it. secret password was the message, or something like this. So we can see those 7361. Yeah, it's here. Yeah. So this is the part of the secret message. So let's send some more requests. So the Alice continue to surf the web. Like for example, so she's going to Google English. So we see an X data sending, which are sent here. So just send few more data. Oh, we can at the moment check how many data were collected by the receiver. So we can go to this. Oh, we just we just collected all the message. So let's see what will happen after the Alice will continue her web searching. Let's go somewhere. Okay, you can see now that the control packet was sent. This control packet means nothing to send. So let's put some more data to the covered channel. So imagine that our imaginary sniffer has sniffed some more data. Any ideas which websites should I serve? Oh, here we can see a control packet, meaning AA was a control packet meaning start new block, because we sent some like 16 segments and we need to reset the sequence field. I'm not going to show you how it will behave when the packets are dropped because I don't have time to configure IP tables to drop the packets, but you can try it at home. So we see that secret password some more. So after Alice searches the web for another 15 minutes, we'll get all the password. Any question up to this point? Any questions? Any questions up to this point? Well, it works really slow on this, with these two virtual machines.
Sorry, I have a small question.
Okay.
Oh, here.
Okay. Oh.
So when you're using ciphers, are you using the crypto API or did you add DES support into your kernel module?
IP is not encrypted. I'm not sure if I understand your question.
So you said now cipher is 0, but if you enable the cipher and you use DES, did you add DES to your kernel module, to your cover channel code, or are you using crypto API?
I found a little des.c file from 1992, which was under public domain, it was written in ANSI. It was very little, and I just compiled it together with the kernel module, so it's statically linked.
One more question.
Yes?
Here. If the company uses masquerading packet filter or something else, your encryption and decryption will be broken, right?
It will be broken because masquerading is changing the ISN numbers. Yes. The same with the HTTP proxy. HTTP proxy is a killer for this kind of channel. But we can use the same skeleton for changing, well, let's say HTTP cookie. At least I hope we can. I haven't tried it yet. I haven't got time. Okay, so any more questions on to the first part? Okay, so we can go to the second part. So one person from the block was asking about what will happen if the Alice starts a TCP dump on her workstation. So this is a good question, and we can make such an experiment. So let's say Alice became a root, and she's doing something like this. Where was it? Oh, yeah. Okay. So one of the send packet, we can see that some data was sent here. Of course, now we can see ASCII data here. So 61, 64, it's AD or something. Sorry? Yeah, probably. Yeah, some ASCII, obviously. It could be encrypted, of course, but just for simplicity, it's not. Okay, what suspicious can you see on this TCP dump? Yeah, this is the SYN ACK packet for this SYN packet. When we look at the acknowledge number, which is here, is different from this number. It should be this number plus 1, but it's completely different. An idea why we have such a situation here? As I said at the beginning, TCP dump is adding, or maybe not TCP dump, but the kernel part of the PF packet implementation is adding its own protocol handler to the ptype all list, which is called PF packet, which is called packet receive function, and this function is just on the same list our PCC handler is also located. So we got the same list and we got two handlers. One is called first and one is called second. So you might think that we need to make sure that our handler is always before the PF packet handler on the list. Yes? But this is wrong. We can try both configuration. Like we can have first TCP dump handler loaded, and then our PCC packet loaded, and the other configuration. And in both cases, we will have this behavior. What this behavior means? It means that for outgoing packets, our handler was called before the PF packets, and for incoming packets, our handler was called also before the PF packets, like TCP dumps packet. Yes. So in both cases, our code was handled the packet before PF packet was handled the code. Right? Clear? So nothing simpler, just to reverse the order, but it won't work. And you might be surprised why. And the answer is that actually the stuff in kernel, the code in kernel has priority over the userland code. So if we have two handlers registered on p-typal list, and TCP dump is of course a userland process. So no matter what's the order of the handlers, both handlers are executed. Both handlers are executed, so PCC, our handler, is always changing the ISN. And the funny thing is that when those two functions I was showing you on the kernel map was calling the p-typal handlers, they are calling them with the same buffer. Like this is the qxmitnit function, which is calling all the handlers for the outgoing packets. And we can see that it clones the SKB, which is passed to the function, to the handler function. Those of you who are programming kernel, Linux kernel, knows that SKB clone is only copying the header, but the data part, the raw packet data are not copied, so they are shared by two SKBs. So SKB2 will have a pointer to the same block as SKB has. So we have two handlers, and one handler is changing the packet. Because kernel has priority, both handlers are executed. Our handler changing the code. The PF packet handler is just copying the data to the userland. So the userland is executing after those two handlers are finish execution. So the userland part of the PF packet implementation always get the changed data. So it always get the changed ISN. So this is a good behavior in this case, because no matter of the order, we always see a changed ISN. So we always see the ISN, which is actually transmitted over the network. But this is bad in that situation, so for incoming packets, because we always see the ISN after PCC has changed them. So we always see the ISN which were passed to the kernel, but these not match the ISN which were on the wire. Right? So this is obviously an easy method to detect the covert channel. So we need to manage to cheat this. So the solution I would like to present is like this. So we are redirecting all handlers through our own function, which will do skb copy instead of skb clone for each skb. To do this, we need to traverse the p-type all list and to replace which all p-type, all function pointers to point to our own CC, let's say CC packet receive, our own provided function, which will do this. And also we need to hook dev@pack function just to catch all future addition of packet handlers. So this is our new function, which we will redirect all the execution to, can look something like this. This is, yeah, something like this. It will first do copy skb to skb2, copy not clone, and then if it's incoming packet, and only then, and if it's not our original, it's not the PCC handler, we are going to call the original handler, like TCP dumps handler, a PF packet handler in general. And also we hook device at pack, so it first executes this code, which, well, it just puts in the function puts the CC packet receive address and saves some data for restoring. Any questions to this idea? Yes?
Wouldn't it be easier to change the real initial sequence number in the TCP code?
I'm sorry, to change what?
The real TCP initial sequence number. And the TCP code has a...
How can you change TCP ISN number?
The TCP sequence number is first generated somewhere in the kernel, in the original TCP code. And it's probably stored somewhere, and you could
so
overwrite the structure.
You're not asking about this, but just, if I understand, you are asking about patching the kernel, like patching the undocumented kernel function, choose secret TCP number, or something like this, so it chooses another number, yes? Obviously, this is a good solution, but it has the problems like, we don't have the address of this function. Yes, so this is not exported function. This is the problem.
Thanks.
I think the ISNs are stored in a slab cache for open requests somewhere. There is,
I'm not sure if I understand you.
there is a storage structure in the slab cache somewhere for newly opened TCP connections.
There is a storage space for storing what?
Yes, in a slab cache somewhere.
Slab cache,
yes.
Okay.
It's stored there. I think it should be easy to change it.
How would you do this?
Locate the cache and walk it to find the connection, and change the ISN in the structure there.
I'm not sure if SKI buffers are stored in a slab.
I think they are.
I don't know. I just don't have the sources now, so we cannot check it. But how? Okay, when would you? Let's assume that it is stored in the slab. When would you do the check?
When the initial packet is sent outgoing.
Oh, but remember, we actually have to change the ISN. We only have to cheat the PF packet implementation. So even if we found the slab, even if it is in the slab, if we change it, we broke the connection, so it won't work. Yes?
Okay.
Any more questions?
Yeah.
Yes?
It seems to me like you'd be breaking any implementation that relies on being able to change the packet contents that's loaded into the kernel at this point. Is that true?
Say it again. I'm breaking all the...
if I've got anything in my stack that relies on being able to modify the contents of the packet,
Yes.
it's now modifying a copy that gets thrown out, yes?
Right, but most of the packet manglers are actually implemented as net filter hooks. But yes, if you choose to implement some other covert channels, for example, it will probably break it. Yeah. No, this is a very good point. Like, if for example PF packets, if PF packets wasn't a passive sniffer, like we have another covert channel backdoor, we will break it. Yeah, but manglers of like IP tables manglers, they are handled by net filter hooks, so we don't break them.
If you're modifying things at this level, why don't you just call the sniffer first if you detect its presence?
Well, I just said, no matter which is called first, the kernel in code has a priority, and no matter which handler will be called first, the TCP dump will see the result after my handler was executed.
No, I think your problem is that both for incoming and outgoing things, the same sequence of handlers is called. What would be needed is a reverse sequence of handlers.
No, it will not work, because even if I reverse the sequence of the handlers, yes, this is what we are asking.
Yes.
So the PF packets will be called first for the incoming packets, yes. So the TCP dumps handler for the incoming packets will be called before our PCC handler, yes.
Okay, but if you can get them in the order, you want them to see the same things that are visible outside. So first it runs through your thing, then it runs through the dumper.
No matter, all will have priority in the kernel, but because TCP is working in the user mode. So
didn't you say that there's something on the stack that copies it out?
I'm sorry?
I thought you said there's something in the kernel stack that copies it out to userland before the userland filter actually runs.
Say it again.
Is that just a... Okay.
Say it slowly. No, say it.
I thought you said that there's something on the kernel stack that runs and copies out the data to a later userland handler.
Yeah, to userland. So PF packet is doing this.
Right, so if it's copied after you change it, oh, sorry, on incoming, it needs to be copied before you change it, of course.
No, because we are using virtual memory in the Linux, so we are just not it's just sharing the same physical page, I think.
Okay.
Or is it? Well, I'm not sure if it's using how to explain why it's not working, actually. But I did. You can believe me. I did try to reverse the order.
Right.
Yes. I'm not sure at the moment if it really shares the memory.
Maybe if it just copies a pointer, that would explain things. But
it seems like copying the pointer, yeah. But I cannot be sure. One thing I can be sure that reversing the order will not work. That's why we need this worried stuff.
Did you test this on multi-CPU systems?
I'm sorry?
Did you test this on multi-processor systems?
Can I use it on UDP?
No. Did you test this? Are you sure that? Because what I think is what happens is that the PF packet handler queues it on a socket, and the socket only gets read when the userland returns. But if you have, I think if you have multiple processors, you can actually have.
No, okay, say it again. Just.
I think if you have a dual processor system or a hyper-threading system.
SMP system?
Yes, then I'm not
I
sure.
haven't tested it on SMP.
Because I'm not sure the ordering you see is will also hold on a multiprocessor system.
It would be interesting to test it on SMP system. I haven't tested it.
Okay.
Yeah, that would be interesting.
I think it won't work there.
It might, yes. Okay, any more questions?
I have one question. Did you consider to use only the timing of the packets as a covert channel? For example, there's this net timing protocol where the timing is measured to 1 millisecond.
Yeah, I've read the paper from MIT about this, but it would be hard to implement it as passive covert channels because we would need to delay the packets, right? Well, I think it will be much more difficult to, because we need to control the TCP timestamp, right? TCP timestamp, yes? This is what you are talking about?
For example, on my computers, they all have this net time protocol, which they use to set the system time precise to 1 millisecond.
Right? NTP?
Yeah, NTP, right. And you would have to manipulate this protocol a little bit, I guess.
Well, it could be a protocol specific. Like, I don't assume that Alice or another user of the workstation computer will use NTP too often. I think it's more common that the user like Alice will use HTTP traffic or something like this. Okay, so let's look at the demo of cheating PF packet. So as it was said, we are not sure if it will work on SMP system, but you might try. But it should work on uniprocessor system. So this is what we have so far. So this value betrays the covered channel. So I will now load the hiding module. We can see that it found the pack address. It's not a big deal. It's just an exported address. It hooked it. The new function is at this address. This is the module delivered function. The new packet received is at that address. And that's all interesting. So now let's run the TCP dump again. It was at 3. No. Oh, it was. Yeah, this is the Alice computer, and I loaded the Nushu hider on Alice computer. So now we are back to, we need to start TCP dump again. Some debugging info from the hider was displayed. You can see that it was detected that TCP dump has added its own handler. Well, PF packet has added its own handler. So let's go somewhere. It was 3, I think. Okay, it works. So we can see this is another SYN packet, this time with the Nushu hider loaded. So we can see some Nushu data. This is actually the ESN empty. So Nushu had nothing to send this time. Nushu empty, ISN empty. And here we see ACK packet, and this is actually this packet plus 1. Yes? Plus 1, it's 006C0400. It's a big endian convention. That's why it's from the reversed. Questions? Okay, so some ideas how we can extend it. up to this point, I was focusing on stealing information from desktop computers. I'm sure we can also use this passive covert channels on Windows computers. Maybe I will write some proof of concept code in the future. But also, I think we can use it to steal information from servers. Servers differ from workstations by not generating lots of requests, but rather by serving lots of requests. So in that case, we would need to change the ISN numbers, but ISN acknowledged numbers, right? So everything the same, but we are not changing ISN sequence, but we are changing ISN ACK. Okay? And then we have a way to leak the information from the server. This was not implemented. And also, if you want a bidirectional channel, so if you would like to have a, backdoor, so we would like to have a possibility to send some commands and to get some feedback, we can also use, we can combine those two. We can combine this one and the first one, so we'll have a bidirectional channel. So we are going to, this time we will not have a passive receiver, we'll have an active receiver, which will put its own ISN here, and our passive covert channel on workstation will put its own ISN, own ISN here in the ACK packets. So this is the client, yes. So we are sending. This is the gateway. We are changing the ISN. We are changing on the client. We are changing the ISN too, and we've got bidirectional channel. Yes, do you agree? Okay, let's go to the detection of covert channels. We have two approaches. We can have a host-based detection and network-based detection. Host-based detection is easier. In that case, to detect additional packet handler, we can have two ways. We can do it in non-elegant way and in elegant way. Non-elegant way would be invasive method, which would require we load a special LKM, which will add some dummy handler and traverse the list. Non-invasive way is more elegant and good for using on production systems. I'm going to describe two methods in a minute. So the question is how to get a list of registered protocol handlers. So I'm not aware of any tool which would provide administrator with this information. I'm sorry? Oh. Okay, so he's proposing using a Perl, but okay, we need to know how to use it. We need to manually check the following list. Well, let's say only p-type all. Let's focus on p-type all because it's most interesting. The problem is that we just cannot use a Perl, open devkmem, for example, device, and just read the memory occupied by this list. We cannot do this because this list is not exported. This variable, this symbol is not exported. That should be first. Sometimes, if we are administrator of our own system, and if we care about it, and if we always care to put a up-to-date system.map file in the boot directory, we can just use this file to locate the p-type all. But if you are a pen testers and we are just want to check some unknown computer, we cannot rely on this file because it's quite often it's not up to date. Yeah, it's enough that the administrator will recompile the kernel and this file is not up to date. So we need a heuristic method for finding the address of p-type all. And the solution I implemented in one of the tool, a commercial tool which is now using by some pen testing company, is based on the following observation. So we are focusing on detecting p-type all list. If we grab the kernel sources, okay, 15 minutes left, right? If we grab the kernel sources looking for p-type all, we will see that only those functions is using it. It means that only those functions know where the p-type all list is located. Those functions in green are exported, so we can know their addresses. So what does it mean that the function knows? What does it mean that the function knows where is the function or is using the function? It means that if we analyze the binary code of the function, we will find the 4 bytes in that function which actually are the address of the p-type all. So we have a simple heuristic method. We are choosing 3 functions like div remove pack, div add pack, and netef receive skb, which we are sure that have the address we are looking for in their body. We are searching through their body, and we are looking for every 4 bytes which looks like a kernel pointer. What does it mean to look like a kernel pointer? It means to be a number which is greater, in most cases, it means to be a number which is greater than 0xC00000. Yes, this is the 3 gigabyte, and the kernel memory is beyond the 3rd gigabyte. There is exception. Fedora Core 2 is an exception, and 3 probably 2 is also an exception, because it's using a 4G memory split patch, which means that have separate memory address spaces for kernel and user mode, but this is another story. Okay, so we are creating the list of numbers which might be kernel pointers from that function, and that function, and then we are looking for the common set. And in practice, this common set is about 3-4 numbers. And then we are just looking for those, we are just analyzing each of these, let's say 3 numbers, if they look like a p-type all list. What does it mean to look like a p-type all list? It means that it points to something like this, and this should look like a packet type structure, right? This is very easy to check if it looks or not. To show you some code which exploits this heuristic search. So let's say Alice has just bought this secret tool. Oh my god, did I forget to put it here? Just a moment. It's really slow. I mean, the VMware and two machines running together are really slow. I have really not too much memory in that laptop. Okay, so we can see here one register handler for Nushu sender. Nushu sender is this is the address of the handler, and Kfinder also makes a lookup to find a module which contains that function. So obviously Nushu sender is something which Alice is not aware of, and it should make her suspicious. We can also list the
Are the symbols like IP receive exported somewhere?
IP receive?
It would be easier to just grab for them and check if they're on some kind of list. Without all that magic.
What do you propose?
Well, on this list, you have pointer to the IP receive, etc.
Yes, I have.
So just grab all the kernel memory
do you suggest
for such functions
to search
and check
one
if at that place it's part of the list.
So do you suggest to look through the, let's say, 16 megabytes of memory in order to find this number, yes?
Sure, that's very easy. That's one line of Perl.
Yeah, but how many false positives did you get?
No. We have some set of positives. It would be just pointers to IP receive. And just look at the next 4 bytes, or what is it, if it's some kind of a list. If it's some kind of a list, you have, I mean, this is just one line of Perl code, as I said.
Yeah, but you still need...
Everything can be implemented in Perl.
But you still need a way to check all the false positives if they look like p-tupole addresses, right? So you still need the same code as Kfinder is using, and searching for this is probably not as portable as searching for those three functions, because maybe in the next kernel IP receive will not be exported. But those 3 functions must be exported because they are API.
You showed already that between 2.4 and 2.6 you had to use different functions, so
no,
maybe
the same
2.6 something.
Well, we always need to have def add pack, def remove pack, and netf receive its skb.
Well, but these 2 kernels use the same network system, and they have different sets of functions. So maybe 2.6.11 will have even different functions.
No, because this is well. Well, this is a well-documented function. Like
right, but
this is changing.
But the documentation only says that this def@pack can be called, but it might call some third function which will do the actual stuff.
Yeah, you're right. But
as you can see, the def_remove pack in the kernel 2.4 did the work, and in the kernel 2.6 calls some other function. So I think that my per one-liner would be better.
But what will happen if they decide to not export IPReceive? I can just only change the name of the function, and what will you do?
Well,
Right, this is not the end. I just have 5 more minutes.
Okay.
Okay, just a few words about network-based detection. I think it would be interesting to implement network-based detection by just having some kind of random numbers fingerprinting tool, because we can expect that although I'm using DES here, which should generate random numbers, we can expect that the PCC-generated random numbers, although they should look like random numbers, they will be somewhat different than random numbers which are generated by Linux kernel for the ISN numbers. Can you go to the microphone? Because he's just saying that it was completely incorrect.
So what you said is not doesn't agree with the cryptographical knowledge, because recognizing that a source of pseudo-random numbers is not generated from the real random source with probability.
But did you heard about tools like Die-Hard?
Yes, but they just depend on the fact that the generators of the sequences were really bad. If Linux used some, well, I'm not sure if it does, OpenBSD sure does use some real cryptographical PRNG for that. I'm not sure if new Linux does that too.
Well, that would be cool. If you're right, that would be cool, because it would mean that it's not possible to detect this channel.
Well, that's only if Linux uses some serious cryptographically secure generator.
Okay, so what he's saying is basically that I'm not able to find any difference between those two random number generators.
Well, if you were, you could break this random number generator.
Okay, that's interesting.
So if you use AES, then recognizing that would be equivalent to breaking AES.
Yeah, but remember that Linux kernel is not using DES.
Well,
okay, we can continue this discussion after the lecture. I just need to finish it.
Here.
So, it will be interesting to check it, if it's possible to fingerprint it or not. Well, it will be interesting. Do I have some few minutes? 2 minutes, okay. Some notes about start modules. As you saw, my PCC proof of concept code is using LKM to load in the code. As I explained to one of you, there are plenty of methods, well, maybe not plenty, but there are a few methods of inserting code into the kernel. The best method is probably exploiting the kernel overflow, which is probably most stealthy way. And we had some kernel overflows in Linux. We also have in Windows. But if we really insist on using modules, we can, for example, use this algorithm for being stealth, like load module, allocate some space, relocate our code, copy to the allocated space, and remove the module. So the tools, like some tools presented in some fake frag, will not detect this. I chose to implement it only on 2.4 because I simply don't like the 2.6 module loading scheme. We can read more about it here. It's a little bit nightmare because kernel is using such a fingerprint to check if everything is correct. So in 2.6 there is no binary compatibility for modules. you need to recompile, you need to have the precompiled kernel to compile your own module. A future work, Windows port of this bidirectional channel implementation, network-based detector to check if he is right or not. Different queries than TCP/ISN. That would be interesting because TCP/ISN has some limitations like masquerading or HTTP proxy. And some greetings, and that's all. Thank you.